Hi everyone, it's Sean, and I'm making this video because recently a lot of my students have been asking me about the thermodynamic potentials and whether or not there's an easier way to memorize them. Luckily, there is, and I am here to explain that. So, the four thermodynamic potentials that I'm going to be explaining today are shown here. We have internal energy, which is a measure of the capacity for a system to do work and release heat. Enthalpy is the capacity of a system to do non-mechanical work and release heat. Helmholtz free energy is the capacity to do both mechanical and non-mechanical work. And lastly, Gibbs free energy is the capacity to do non-mechanical work alone. So these are the equations for each of these. You'll see internal energy is U, enthalpy H. Helmholtz free energy here we are describing with A. Often you'll see it as F, often A. It kind of goes back and forth. I'm using A for the sake of this video. And Gibbs free energy is G. And to the far right, we have their natural variables, which they are often defined in terms of. And these will make a bit more sense further down. I should explain that I use Ni in the squiggly brackets because this is the number of moles, and it's often left off because, well, you'll see why in a bit. So, these thermodynamic potentials are used to describe the difference between two states of a system. So often they are put in terms of their differentials. So yeah, this is just a bunch of equations, but don't worry. So over here we have how to define each of these variables, what they mean, and then as you go back, these are the differentials. And you'll notice each of them have the same mu dn term at the end of it, and this is the chemical potential times the change in the number of moles. And as I said, this is often left off because it is the exact same for each of them, so it's kind of understood. But generally, we just leave that off. So now, yeah, this is kind of complex, wouldn't you agree? There's got to be some easier way to memorize these and some way to concisely put them down. And that is exactly what I'm bringing you here today. We have the thermosquare. So for this, all you need to remember is vat, ugg, ship. Just think of a big old vat full of Uggs, you know, the old boots that used to be very popular, and then it's floating on a ship, and voila, you're there. So, how to use the thermosquare is the next question. Well, you'll notice that each of the potentials is along the sides of the square, and each of the state variables is along the corner. So, for instance, if we wanted to determine the differential of G, you start opposite it at the corner and you come towards. So, G is going to be minus S dt plus V dp. And so if we look, here we have dg is minus s dt plus v dp. It's exactly as our thermosquare predicted. I'll do another one for you. We'll look at the Helmholtz free energy, A. And this is actually why I use A instead of F, just so I can remember vat ugg ship, because vift ugg ship doesn't sound quite as good. So we have A. According to the thermosquare, it should be minus s dt minus p dv. Sure enough, minus s dt minus p dv. So yeah, it looks like the thermosquare covers everything we need it to. But something's missing, isn't it? What about chemical potential? Well, don't worry. Conveniently, there's actually also a very easy way for us to remember that, and that is what the rest of this video is going to be about. And that's what this is. This is essentially the thermodynamics cube. Obviously, it's not a cube because it's this crazy shape, which doesn't even have a real geometric meaning. But this is the three-dimensional version of the thermosquare. So what we have here is that on each of the triangular faces, we have one of the thermodynamic potentials that we're trying to remember. And on each of the square faces, we have one of the thermodynamic variables that we put them in terms of. So just like the thermodynamic square, this works exactly the same way. So you put what you're looking for on top, and then here you have to go across from the bottom to the top. So U is minus P dV plus T ds plus, where is it, mu dn. And so that covers all three sides, and you have to do that for each of them. For instance, we have Helmholtz free energy. Once again, you start from the bottom and you go across the cube to the top. So we have minus s dt minus p dv plus mu dn. And there you have it. You can use this to determine any of your thermodynamic potentials. Just gotta set the triangle on top, go from the bottom across to the top, and you will have your answer.